Are we hurtling toward disaster beneath Naples? In the shadow of Vesuvius lies Campi Flegrei, an ancient supervolcano whose restless ground is now revealing an unsettling secret. The great cracks and faults hidden beneath are slipping with unprecedented speed. Recent studies using everything from advanced seismic mapping to fluid-filled rock experiments paint a clear picture. The subterranean plumbing of Campi Flegrei is under incredible stress. Fault lines are moving, and the entire system is accelerating. Scientists are asking what processes are driving this turmoil and how close is the caldera to a critical tipping point. The answers are as fascinating as they are alarming. Nestled on the Bay of Naples, Campi Flegrei, burning fields, is a broad, sunken caldera, roughly 12 kilometres, about 7 miles wide. It sits under bustling towns like Pozzuoli and 1 million people. Together with the nearby city of Naples, around 1.5 million people live within range of its fury. Over the last 2 centuries, the caldera has been mostly quiet, but its record is fearsome. Around 40,000 years ago, it unleashed Europe's largest known eruption, and another massive blast about 15,000 years ago. Now, decades of careful monitoring have revealed signs that the volcano's gentle stirrings might be gathering force. Since about 2005, Campi Flegrei has been in a state of slow unrest. The ground has been bulging upward, small earthquakes have been rattling residents, and gases have been seeping. In late 2020, scientists noted that these changes were not constant, but accelerating. High-precision GPS measurements show that by mid-2025, the centre of the caldera had risen over 1.46 metres, nearly 5 feet, since 2005. This increase is not linear. The uplift has been growing faster and faster, like the curve of a balloon being rapidly inflated. For much of the 21st century, the land around Pozzuoli rose only a few centimetres per year, but reports now cite rates up to 3 centimetres per month, roughly 1 1/5 inch per month, during the most active periods. Meanwhile, seismic records reveal that earthquakes, which were once mere trickles of tiny tremors, have surged. 5 quakes above magnitude 4 have rattled the caldera in 2025 alone, including a magnitude 4.6 event in March, the largest since modern instruments were installed. These accelerating trends are crucial clues. Geological analysis shows that Campi Flegrei's crust is behaving in 2 phases. At first, it deforms nearly elastically, like an inflated dome, as pressure from below builds. But now it is transitioning into an inelastic regime where cracks form and faults move. A detailed study of data from 2000 to 2023 found that the uplift follows a parabolic curve, and the number of quakes is growing even faster than exponentially. In plain language, the caldera's spring is being wound tighter year by year. Researchers interpret this as the shallow crust progressively weakening under the relentless pressure of molten rock and superheated fluids. At each step, new strain is added to the system faster than the old strain can relax. So when the ground does move, it releases a burst of seismic energy. This feedback, likened to the Kaiser effect in rock mechanics, means that each uplift and quake cycle lowers the rock's resistance to the next one. In other words, every throb of the ground is making it easier for the next pulse of stress to trigger more movement. Hidden beneath all this unrest are the faults, fractures in the crust where sides can grind, slip, or open. Recent breakthrough work using artificial intelligence to re-examine Campi Flegrei's seismicity has uncovered a shockingly intricate fault network that was invisible to scientists before. By crunching decades of noisy earthquake data, researchers discovered tens of thousands of tiny quakes that had been missed. These numerous quake records reveal a ring-shaped fault encircling the region of uplift around Pozzuoli. A crisp, circular break hundreds of meters wide, partially under the sea. Even more striking, two major faults were found converging deep beneath Pozzuoli town. Geologists warn these faults are no minor cracks. Their geometry suggests they could host earthquakes up to about magnitude 5 if they rupture fully. In effect, the ground has been quietly mapping itself. As pressure builds, older weakness zones are lighting up, showing where the crust is letting go. The pattern makes sense in the context of the volcano's internal plumbing. Below Campi Flegrei lies a stack of layers with different properties. A caprock, a sturdy fibrous layer about 1 to 2 kilometers deep, acts like a sealed lid on the system. It traps supercritical water and carbon dioxide, CO2, pressing up from below. Beneath that is a gas and fluid-rich reservoir, roughly 2 to 4 kilometers down, often called the caldera's lungs, which fills with hot, volatile-rich magma or hydrothermal fluid over decades. Laboratory experiments on rock samples from these depths show this reservoir volume swells dramatically as fluid pressure increases. In turn, the expanding fluid body pushes upward on the caprock, causing the surface to bulge. However, this build-up doesn't remain hidden. As pressure mounts, the caprock eventually starts cracking. The deepest recorded quakes, up to magnitude 3.5, have occurred right at the edges of that reservoir where older faults lie. As the gas reservoir deflates slightly, for example by releasing fluid up a conduit, the lateral support on those ring faults weakens, allowing them to slip. Thus, hydrothermal pressure is a key driver. Geochemists and geophysicists note that Campi Flegrei's unrest is fluid-driven, not so much a blob of magma poised to erupt imminently, but rather a system of pressurized steam, gases and melted rock interacting with brittle crust. When fluids rise, they heat shallow rocks, increase pore pressure and effectively lubricate faults. The result is a chain reaction. Rising fluids cause fractures which release more pressure, causing more fluids to upwell. Each shallow tremor or series of bursts, known as volcano-tectonic swarms, is often the sound of this release valve partially opening. Since 2021, scientists have even observed burst-like clusters of quakes with almost no break between them, an unusual pattern that elsewhere signals a critical heating or pressurization of the system. Such rapid-fire swarms have been tied in other volcanoes to near eruptions or explosive steam events, phreatic blasts. In Campi Flegrei, these swarms have migrated around the caprock region and correlated with zones of anomalously slow uplift, places momentarily lagging behind. This suggests localized cracking and fluid escape are actively modulating the uplift. Crucially, the faults themselves are responding to all this. For decades, the caldera's uplift was nearly axisymmetric, a smooth, round dome of rising ground over Pozzuoli. Lately, that perfect symmetry has broken down. Since about 2023, monitors have recorded a small but telling tilt. One side of the dome rises slightly less quickly. Geologists interpret this as the sign of a new normal fault forming or reactivating beneath the surface, often dubbed a volcano-tectonic fault. In this case, the fault plane has an orientation roughly west-northwest, near azimuth 249 degrees, striking steeply north-northeast. On this plane, the hanging wall, the block above the fault, is moving down toward the northwestern coast of Pozzuoli. Think of it like a little slice, dropping down into the caldera basin. This preferential fault has been inferred from the clustering of mid-depth quakes along a consistent plane, plus the slight geomorphic tilt in the uplift pattern. It is as if the central dome is beginning to crack in one direction, making the eastern side give way under its own weight. How does this fault slip affect the volcano's behavior? Normally, on a volcanic dome like this, the maximum vertical stress is up-down. It's like piling heavy weight at the top. Introducing a normal fault, a crack where one side drops down, actually relieves some of that weight by displacing material downward. The newly slipping block is effectively shoving itself out of the way of gravity. Paradoxically, by letting that slice of crust fall, the uplift in the remaining central block can accelerate, because the pressure has fewer rocks to support. Models suggest that as this normal fault grows, it will allow the uplift to become even more efficient. Each slip will lower the effective load, and the central bulge can rise a bit faster. We see this in real time as the uplift no longer being perfectly round. On the other hand, the dip of the new fault, sloping inland toward higher ground, means it's somewhat clogged by gravity. It's harder to move heavier rocks upslope, so its slip may be slow for now. In any case, scientists caution that the growing fault could become a preferred pathway for fluids, channeling steam and gases in new directions, which could change eruption or hydrothermal patterns in the future. All these clues, accelerating uplift, quakes and widening faults, point to a physical picture. The caldera's shallow crust is creeping toward failure. In geophysical terms, the system is showing signs of stress accumulation and plastic yielding. Rock samples and analog experiments tell us that as rocks are strained, especially in the presence of heat and water, they initially stiffen but eventually soften and fracture. This softening means that small triggers, a minor earthquake or new magma intrusion, can produce larger movements than they would in an unstrained state. The exponential rise in earthquakes suggests exactly this. Each incremental rise in pressure now unleashes disproportionately more cracks. In a failure model, the energy added is not stored as efficiently as elastic energy. Instead, it is expended in creating new fractures or moving existing fault blocks. This is visible in the statistics. The relationship between uplift and quake count has steepened over time, consistent with rock behavior that goes from elastic, where deformation grows slowly, to viscous or plastic, where deformation happens at roughly constant stress. Why say dangerous levels? It's because this suite of processes, rapid pressurization, mechanical weakening and active fault slipping, historically precede major transitions in volcanic behavior. While no one can precisely time an eruption, the warning signs are hard to ignore. The caldera's behavior is echoing past crises. In the early 1980s, a rapid intrusion of magma led to chaotic uplift and explosive events, ultimately the 1538 eruption. Now, instead of a single magma pulse, we have sustained inflation driven by gases and shallow magma, but the endgame could be similar if pressure continues climbing. Advanced failure forecasting methods used for volcanoes rely on accelerations in measures like deformation and seismicity. By that metric, Campi Flegrei is racing. If current trends held, we might soon be in the same ballpark as the 80s level of strain, the point at which the next eruption becomes a distinct possibility. All the while, each minor earthquake along those newly revealed faults is a sobering note. Fault slip isn't instantaneous. It can happen in small steps or creep, slipping a few centimeters one quake at a time, or in sudden jolts. In Campi Flegrei's case, many of the recent quakes are quite small, often below magnitude 3. but their frequency and clustering say that slip is continuous. Imagine dozens of tiny shifts along a crack every day. Cumulatively, that's equivalent to a more noticeable rupture. Instrumentally, this shows up as short inter-event times, almost rhythmical popping of cracks, which geoscientists link to systems on the brink. These could correspond to piecewise sliding of the nascent fault, or to pulsing fluid pressure. Regardless, it's all part of the same mechanism. Each quake lets a little fluid escape or rock give way, which then lets pressure rebuild, and so on. Meanwhile, deeper processes lurk. Geophysical imaging finds a denser, carbonate-rich basement rock beyond about 4 or 5 kilometers down, a stronghold beneath the caldera. That basement supports the volcanic system like a foundation. Its presence explains why shallow magma hasn't broken through the caprock yet. The fluids have nowhere to go but sideways or up along faults. So what happens is that pressurized water and CO2 seep through cracks, heating the shallower rocks to boiling point. Degassing of even a small amount of magma, or long-dormant magma, can dramatically raise pressure. Studies, including borehole core analyses, show microscopic fibers and clay in the caprock, which can expand with water. These can account for sudden local tilts when they wet up. Thus, much of the slip could be hydrothermal, water steam pulling rock apart rather than chunks of magma bursting through. If this continues, the caprock itself might shatter in places, possibly leading to phreatic blasts, steam-driven explosions that have no warning and send ash high into the sky. In a sense, Campi Flegrei has entered a feedback loop. The rising tides of gas expand, the rock cracks, the rock slips, then more gas escapes through the new paths, adding to the uplift elsewhere. Each component, the fluid reservoir, the caprock, the faults, is interacting in a complex web. The recent research shows these interactions clearly. For example, one study found that when earthquakes rupture fast, the surrounding rock suffers extra damage, reducing shear strength and making the crust more prone to slip next time. In our case, the abundance of small shocks suggests that much of the seismic energy is going into off-fault damage, breaking the surrounding rock, rather than just sliding one block over another. This makes the entire upper crust progressively weaker. Put together, all this science indicates one message. The subterranean machinery of Campi Flegrei is running hot and fast. The faults that once moved imperceptibly, little leaks in the dam, are now sliding more readily. The brakes that hold the dome steady are loosening with every uplift event. It may sound ominous, but this is the language of geologic processes. The slip of a fault is simply the rock responding to the loads we place on it. But the speed of that slipping is our alarm bell. So, what might this mean for people? If nothing else, it means that scientists will be watching every millimetre of ground movement and every minor tremor closely. We can't say that an eruption is certain or imminent, but ignoring these trends would be foolish. Many volcanoes show a calm before the storm behaviour similar to this, years of unrest followed by a big event. The difference here is that we have unprecedented monitoring. We can literally see cracks opening and stress climbing. This allows us to anticipate rather than be taken completely by surprise. For now, the protocols at Campi Flegrei call for warnings if certain thresholds, uplift rates, gas release, large quakes, are exceeded. It's clear we are trending toward those thresholds faster than ever. For geologists and volcanologists, Campi Flegrei is a live laboratory. Every new pattern of faults and every spike in ground motion is a clue. The technical details, caprock fracturing, fault dip angles, stress measurements, fluid pressures, are all pieces of a puzzle that, when assembled, will give us a deeper understanding of how calderas awaken. Already, methods that combine seismic imaging, satellite data, and even AI-enhanced earthquake catalogues are giving unprecedented clarity. These tools have uncovered the physical explanation behind the popular phrase, "Campi Flegrei's faults are slipping faster." In the end, the caldera's story is a cautionary tale in the making. Outwardly, nothing dramatic may happen tomorrow. No curtain of fire is visible from the city squares. But underground, an unseen drama is unfolding. The rocks beneath are groaning under pressure, old breaks are widening, new ones are cutting through, and fluids are pouring fuel on the fire. The delicate interplay of these processes is what geologists call volcanic unrest. It may yet settle down, or it may build into something larger. Either way, the evidence demands attention. Campi Flegrei is reminding us with every silent slip and every inch of rise that even when a volcano sleeps, it does so lightly, and sometimes it does not sleep peacefully at all. If you like this, hit like, share it with a friend, subscribe for more, and tap that hype icon. Let's keep the momentum going.